Welcome to surface area of a rotated polar curve. So the idea here is just like with arc length, we will consider our polar curves as sort of parametric curves. So we can again view our polar curve as a parametric curve. Okay. We have if r equals f of theta, then we have again x equals r cosine theta, or f of theta cosine theta. And y equals f of theta sine theta. For parametric curves, if we rotate it about the x-axis, then we had the surface area was equal to 2 pi times the definite integral from a to b of x of t times the square root of dx dt squared plus dy dt squared dt. And if we rotated about the y-axis, we had surface area equal to 2 pi times the definite integral from a to b of y of t times, sorry, I have these backwards. For x, it should have been y of t, and for y, it should be x of t. So surface area for rotation about the x-axis should have been 2 pi times the definite integral from a to b of y of t. For the y-axis, we should have x of t times the square root of dx dt squared plus dy dt squared dt. Now, the x of t and y of t in polar will just be f theta cosine theta and f of theta sine of theta. Right? So the y of t is just f of theta sine of theta. X of t is just f of theta cosine theta. And then in the previous video, we saw that dx dt squared dy dt squared was just f of t squared plus f of theta squared plus f prime of theta squared. So we get a quick formula now that we already had the arc length simplification. We get a quick formula for our surface area. And it looks like I need to update my screen. 1 moment. All right, so again, that dx dt squared plus dy dt squared is just f of theta squared plus f prime of theta squared, as we saw in our arc length video. So we wind up getting, if we have the polar curve r equals f of theta on the interval from theta 1 to theta 2. If we rotate about the x-axis, then we have the surface area is equal to 2 pi times the definite integral from theta 1 to theta 2 of f of theta times sine of theta times the square root of f of theta squared plus f prime of theta squared d theta. And if we rotate about the y-axis, we have that surface area is 2 pi times the definite integral from theta 1 to theta 2 of f of theta times cosine of theta times the square root of f of theta squared plus f prime of theta squared d theta. So this is how we can go about calculating surface area from rotating a polar curve. So for example, let's find the surface area of the rotational solid formed by rotating the upper half of the cardioid, r equals 1 plus cosine theta, about the x-axis. So our cardioid looks somewhat like a sideways heart, a curved sideways heart, sort of sideways on the x-axis. So if we take the upper half of that and then rotate about the x-axis, we get our sort of interesting rotated shape. Okay? And we can find the surface area. So the upper half of the cardioid goes from theta equals 0 to theta equals pi. Pi is what will get us an r of 0. Okay? So we're interested in our interval of interest. Is 0 less than or equal to theta, less than or equal to pi. R is 1 plus cosine theta. So 1 plus cosine theta is our f of theta. So we have f of theta as 1 plus cosine of theta. That means that f prime of theta is negative sine of theta. So we get, and then we're rotating about the x-axis. So we have, therefore, the surface area is found by taking 2 pi times the definite integral from 0 to pi of f of theta times sine of theta times the square root of f of theta squared plus f prime of theta squared d theta. If we go ahead and plug things in, we are looking at 2 pi times the definite integral from 0 to pi of f of theta was 1 plus cosine theta. So we have 1 plus cosine of theta times sine of theta times the square root of, let's move this whole thing so that I have more room to write. So times the square root of, we have f of theta squared, so 1 plus cosine of theta squared, plus f prime of theta squared, so this is a negative sine of theta squared d theta. This is 2 pi times the definite integral from 0 to pi of 1 plus cosine of theta times sine of theta times the square root of cosine squared theta plus 2 cosine theta plus 1 plus sine squared theta d theta. And we could rewrite this as 2 pi times the definite integral from 0 to pi of 1 plus cosine of theta times sine of theta times the square root of cosine squared plus sine squared gives us another 1. So we are looking at 2 plus 2 cosine of theta. And then d theta. Once again, I'm going to go ahead and just plug this into Desmos to evaluate what that surface area is. If we plug this into Desmos, we wind up getting approximately 20.106 square units as our surface area. So again, ultimately, it's just a matter of plugging into the formula, knowing what your f of theta is, knowing whether we're rotating about the x or y axis, and what the boundaries are for the theta. Once you are plugged into your formula, you are welcome to then use Desmos to do the final computation for these application problems.